But good morning, everyone. Thank you, Covaris, for inviting us to show the work we've been doing. I'm Meagan from AstraZeneca, and I've been working with my teammate, Juan, to simplify our homogenization workflow and maximize our protein extraction and minimize sample variance in the mass spec analysis using dry pulverization and the AFA technology that we're all here to hear about. So the motivation behind the work that Juan and I have been doing is that our current workflow for processing tissues, which is using a bead beading with a bead mill, is prone to variability from incomplete or inefficient protein extraction, as well as pretty significant heat generation in each cycle. From heat generation, which can damage your proteins, which is going to affect your downstream confidence in your data. Furthermore, it's pretty time consuming. There's a lot of hands-on steps. And you're also with the consumables that are available for specifically the bead mill that we have on site, you're limited in the amount of tissue that you can actually process. And so what we wanted to achieve with this work is to optimize the AFA parameters to maximize the extraction and decrease variation, as I've said, as well as to demonstrate improved data quality relative to our standard B-mill treatment, and then also to reduce the fraction of workflow that involves active sample handling, as Jen said in her talk, that with each of those transfers, each of those steps can just increase more and more variation. And so the way I'm going to present this work is to give a very brief overview of the AFA technology as well as the dry pulverization using the CPO2. I'll then show the experimental design and describe each of the parameters at each step that we've been working on optimizing. And then we'll take a look at some of the data and how well we're extracting the proteins from our tissues, as well as the coefficients of variation in our protein identifications. And then just briefly at the end, we'll talk about whether or not we achieved our goals and what we're going to be doing moving forward. So the two technologies that we're working with are the dry pulverization, and for that, we're using the CPO2 cryoprep from Covaris. And this device, it uses mechanical force, basically a very, very intense hammer, to smash your flash frozen tissues. And what this is going to do is take your nice tissue chunk and turn it into a very fine powder. And this process, it's going to disrupt the extracellular matrix and increase the surface area, which is going to reduce the distance that the lysis buffer has to get into your sample in order to extract those proteins. And then for the AFA, so the DNA shearing and homogenization, we're using the LE220RRC. I'm not going to say that anymore in this presentation, but focused ultrasonicator. And within the fleet that Covaris has put out, this is the fastest system, and it can be integrated into many workflows, such as proteomics, which is primarily what Juan and I do on our team. And as Samir said at the little beginning intro, AFA energetics localize ultrasonic acoustic energy into a very focused point on your samples, which is going to give you that very, very efficient and effective protein extraction. Okay, so the steps that we use in our workflow are to first weigh out the tissues, which we then transfer into a tissue tube, one of the consumables that Covaris has. We then flash freeze our samples, and we call them smashing it, but smashing it using the cryoprep or cryofracturing. And we do that 2 rounds just to really maximize the pulverization process. And then from there, we transfer our powdered sample into a 1 ml millitube with the AFA fiber. You can see that line right there. That's actually a little tiny glass rod. And that's in there to improve the mixing because we're working with fairly large sample amounts. And then downstream, we do BCA analysis to quantify our protein concentrations. and then go forward to global proteomics, the standard workup, digestion, alkylation, cleanup, yada, yada. And so for this work, we're using the protein extraction as well as the covariance in our protein identifications as metrics to evaluate our optimization work and how well the system is working for us. And so, while diagrams are great, I thought it would be valuable to show you what this actually looks like in the lab. And so here you see one of us, we're holding a tissue tube, and you can see here there is a chunk of tissue that has been placed in there. We then have come up with this. This is being optimized. This is kind of a bit of a brute force setup. But we flash freeze our samples in liquid nitrogen for about 30 seconds. However, because of this setup, we're able to just kind of go one at a, we don't have to wait except for the initial 30 seconds. And then so after we've smashed the tissues in the tissue tube, we transfer them to that millitube AFA fiber. So you can see the fiber here, and you can see how, how fine this powder is from this chunk, which I wish you could see that better. And then to the powdered tissue, we're going to add our lysis buffer and mix it up a bit. And then we do heat denaturation prior to our AFA treatment. And then we do repeat that afterwards, just to really make sure we've pulled out as much protein as we can. So the parameters that we are exploring with the AFA and in this work are the peak incident power, or PIP, the duty factor, and the cycles per burst. And this is just a very simple graphic to kind of give you a reference for what those are. So the PIP is going to be the amplitude of those acoustic waves that the sample is subjected to. So how powerful are we hitting it? The duty factor is going to be how long the sample is actively treated with the acoustics during a single cycle. So here, this is approximately a 25% duty cycle in this representation. And then the cycles per burst, that's going to be how many acoustic waves that we hit our samples with at this PIP within each burst of treatment. And the duration of these cycles or bursts is going to be determined by the frequency of the treatment. So the first step to any method development is going to be setting a baseline, as well as comparing it to the standard workflow that you already use. And so the parameters that we decided to use for this are to 1 milliliter, because we're using the 1 milliliter tubes. Then we also decided to start with the 350 watt PIP. And this isn't specific for the consumables we're using. This is what Covaris has recommended for the TPX PCR plates, but we just thought it would be a good starting point. And then using a slightly higher duty factor than for the cell workflows, and then also setting the cycles per burst to the maximum option that you can use, and that's going to be 1,000 cycles per burst. And then just so you know what our reference or comparison point is with the bead homogenization process. And this is not meant to be representative of everybody's workflow. This is just what we have done in our lab. But what we do is we add our tissue chunk into a homogenizing ceramic bead consumable, and then we do about 3 to 5 cycles of bead beading in our bead beater. And the reason we only do 10 seconds is to avoid that heating that I mentioned at the beginning. And then we have to take the samples out, we let them cool on ice before we move on to the next iteration of bead beading. And then after and the reason I say 3 to 5 cycles is because it's kind of an eyesight, you're looking at it. Does it look like it's been homogenized well? But there's not really a analytical metric for that. It's just kind of visual. But after we've done that, we do the heat denaturation, and then we spin down the samples and then move forward with our downstream prep. So just before I get into the actual results, I do want to just make a bit of a disclaimer. So the consumables we used for our dry pulverization was the TTO5 extra thick tissue bags. And these are rated for 50 milligrams of tissue max. And while Joanne and I tried our best to weigh 50 milligrams, we did, there was a loose tolerance of about plus or minus 10 milligrams. And so there's probably samples that exceeded this tolerance despite our best efforts. And so, some of these results we're really testing the limits of these consumables. But this is actually great because our ceramic bead consumables, the maximum for that is also 50 milligrams. So this work is all testing the maximum limits. But I do just want to say you should take these results with a grain of salt. Science is an iterative process. Okay, so our baseline comparison. I have our methods, the methods that I just described, manual and our first burst. And I'm going to be showing this table for all of our results. And the values I'm showing are the number of replicates that we did for each, and then the mean protein, extracted protein concentration, as well as the median, just because that's a good representation of the reproducibility, and then also the percent CV. And in these tables, that's going to be the covariance in our extracted protein concentrations. And then in the box plots, this gray box over here, which I'll show for all the figures, is kind of the range of maximum extracted protein if we're operating under the kind of colloquial assumption that for every 10 milligrams of tissue, you're going to get out a milligram of protein. And so we can see here from just our baseline where we're testing out, just kind of starting somewhere with AFA parameters, we are achieving a slightly higher protein concentration extracted, and we do see that there's less variance, so more consistently extracting proteins from quite a few samples. But we want to know downstream, does the mass spec data quality improve? And for this, we did not see improvement. So here in these distributions, I'm showing the percent covariance in our protein groups that are identified by the mass spec analysis. And the dashed lines aren't showing up super well, but that's okay. So these four traces, I'm showing the two AFA, and S1 and S2 is just because Joanne and I separately prepped about 12 samples in parallel. So this is further representative of the reproducibility as well as our scientific skill, I guess. But what we can see here is that with the manual, the bead mill, we were able to get lower than 20%, which is kind of our benchmark of what we're aiming to get. While the AFA treatment, it was higher than what we would like to see. So, we were like, okay, we need to try changing some of the parameters. And so going back to those parameters that I've described, what we anticipated is that obviously if we optimize these, we're going to get better protein extraction. And then furthermore, we still want to see if the data, can we achieve better quality data? So our first tissue that we worked with is liver tissue. And so we had a couple of different AFA treatments that we wanted to compare. So here I have the manual steps, and then the parameters that we're really testing here are one, the PIP. So we tested the medium, which is kind of lower, and then also the Covaris protocol, 350 watts. And then we also wanted to test the dithering, which I will touch on a little bit later in the process, but it's basically the direction of the movement of your samples during the AFA treatment. And then also the number of heat cycles that we treat our samples with. Okay, so now that you see these three different methods that we tested, these are the protein extractions. So here I'm showing the same results from the manual, where we're getting, it's about 50% of what we would expect maximum. But with all three AFA treatments, we're getting right in, like we are extracting all of the protein that we possibly can. And what you can also see is, as I said, we exceeded the limit a little bit, but what this data is showing is that we're still able to get more protein out. And in general, we're getting at least 2 times the amount of extracted protein compared to our manual bead mill treatments, as well as considerably lower covariance in those extracted amounts, specifically for AFA1. And so looking at the mass spec data from these results, we see that AFA1 is also giving us really great CVs. So that was pretty exciting. And so we decided to move forward with this AFA1, and these are those parameters, to test on different tissue types of varying hardness. And so the different tissues that we worked with in this next round were liver, brain, kidney, spleen, and heart. So quite a few. And this is just a kind of relative hardness or softness. So heart is going to be the hardest tissue that we've worked with. And just to remind you, these are the parameters we're using. And so for spleen, this method did work well, but you can see that the CVs weren't as great for these other harder tissues. And so we were like, okay, let's go back and kind of revisit these parameters that we have the options to change. And so this is where the Z dithering, or the dithering, comes in. Here we tested 6 different AFA methods, and for what I really want you to focus on here is that in AFA 5 and AFA 6, what we've actually introduced is dual dithering treatment. So we'll do one round of Y dithering, which is shown here. We're doing 1 millimeter at 20 millimeters per second. But then after 4 minutes of treatment at this dithering, we switch to the Z direction, so that's up and down. And what you can see in these videos is the tissue, it's being very well mixed. And we just thought by adding the different direction, we might be able to further interrogate those samples to get the protein out. And this is reflected, I would say, in our data. So what we see here, and this work I did with the kidney tissue because that gave us the worst results with our initial method. What you can see here is with AFA 5 and AFA 6, we're again extracting basically the most protein that we can, and we also achieved pretty great, CVs. So AFA 4, which actually doesn't have the dual treatment, we got below 20%, but also with the AFA 5, we were able to get below 20%. But we chose to go forward with AFA 5 and AFA 6 because we knew that AFA 4 didn't give us the best results previously. Okay, so we applied that AFA 5 and 6 to some of those previous tissues that we had issues with. And with those treatments, mid and high, those are, mid and high is representative of the PIP, so the amplitude of treatment. We see really great extraction, really tight distributions, so very consistent and very effective. And we also see that for all of the treatments that we tested, we're within that threshold of covariance that we want to see at the mass spec level. And so we decided to move forward with AFA 5 to test on different tissues. Slight caveat about this prep, this is one I did, and there's a lot of scientists in AZ, so sometimes it's hard to get in the queue. So these samples actually sat for quite a while. They kept getting pushed back in the queue, and so there was some evaporation, which is going to increase the variability, unfortunately. However, what we can see is that the protein extraction, which isn't going to suffer from this issue, we are still getting really great extraction levels. And then even in the mass spec data, all things considered, the CVs were still pretty close to that 20% benchmark that we wanted to see. So, this work has been, it's moving in the positive direction, but it's still not perfect. And then the last thing, in my objectives of this work, I mentioned that we wanted to reduce the amount of active hands-on time. And these tables, they're pretty busy. There's a lot of steps, of course, but what I'm showing here is the amount of time for each of these steps for each sample, and then as well as the total time that's required for that step, and then whether or not it's actively hands-on. And so you can see for the bead mill, a lot of the steps are hands-on, whereas with the AFA treatment, there's a big chunk where you're not actively handling your samples. And so with these rough estimates, for bead mill, it's about 70% where you have to be there with your samples and actively engaging with them. Whereas with the Covars, it's reduced down to 33%. You can put your samples into the AFA, you can walk away, and you know you're going to get all of the protein out that you can. So just in conclusion, I just wanted to revisit the objectives that I put forth at the beginning and whether or not we were able to achieve them. And yes, we were able to optimize the parameters, and even though there's still room for improvement, it's still better than our bead mill. We consistently get over 2 times the protein extracted. And then also demonstrating the improved data quality. Yes, we were able to do that. We were able to get the liver tissue to reduced from over 15% to less than 10%, which is really awesome. And then, the active hands-on, the fraction of time spent homogenizing with the AFA is completely eliminated. So that's really great. So moving forward, our key takeaways and next steps. So the Z and Y dithering, while it is improving our extraction and reproducibility, our current method did correspond to a 60% increase in treatment time. And it's probably not necessary to do 4 minutes of treatment at each of those ditherings. So we're going to try shortening that treatment time to further improve our throughput. And then, as I said, with the testing the limits of our consumables, so we're probably going to move to the TT01 tissue tubes and the 2 milliliter millitubes for the AFA, so that way we're within the bounds of the consumable range and application. So with that, I forgot to put an acknowledgement slide, but I would like to thank AstraZeneca, my teammate Juan, my teammates at ASMS for having us here today, all of you for attending, as well as Covaris for inviting us to show this work, which has been really fun. Yes, that's it. That's the end of my presentation. Thank you.